Hi, in today's video I would like to introduce you a very nice problem regarding arithmetic and number theory. Here is the setup. We have this fraction 2 to the 3n plus 1 is divided by n squared is an integer. Okay, the question: find all solutions for all positive integers. Okay, in fact this problem was given as an international mathematical Olympiad of year 1990. So it was given as 2 to the n plus 1 is divided by n squared. So what I have done here, just I have made some changing in exponents, changing from n to 3n. Okay, so the problem was almost the same, just there is an extra tricks here. Okay, so I have given the following hints. You can apply Fermi Theorem and Bayesian Theorem. First of all, you can try the first obvious cases, and the second thing, you are going to use the Fermi Theorem. If you have p as a prime, is not divide a as an integer, equivalent a to the p minus 1 congruent to 1 mod p. So the third, hence use the Bayesian theorem. If you have a linear combination operator x and y as a natural number, so ax plus by equal to gcd of these numbers. Let's get into the solution. So now I have this fraction to the 3n plus 1 is divided by n squared is an integer. Okay, so now I'm going to check the first case. If n equal to 1, equivalent 2 to the 3 plus 1 is divided by 1 square, which equal 2 to the 3 is 8 plus 1 is 9, so 9 is an integer number. Here is the first solution as n equal to 1. So let's try the second solution if n equal to 2. So this one, 2 to the 3n, which is 3 is multiplied by n, which is 6 plus 1 is divided by n to the 2, which is 4. So 2 to the 6 is 64 plus 1 is 65. 65 divided 4. 65 divided by 4 is not a natural number. So n equal to 2 is not a solution. Okay. When we have n is superior or equal to 3, if you take a look at this expression, we have 2 to the 3n is an even number. Okay, so implies 2 to the 3n plus 1 is an odd number. Okay, so since n squared is divided 2 to the 3n plus 1, that means n squared is an odd, because the only odd number 2 to the 3n, so the only odd number which can divide odd number. You cannot find the even number divide odd numbers. Okay, so since n squared is an odd, so that means n is an odd as well, because n squared is a multiple of n. Okay, so this is, we know now n is an odd. Let's p to be the smallest prime such that p divide n. So at since both numbers n and p are odd numbers, at some points p can divide n. Okay, so we choose the smallest prime they can divide n. We don't know yet what's the value of p. Okay, since p is divide n and n square is a multiple of n, this implies p is divide n square. Okay, since p is divide n square, and we have two things here. We have this n square is divide 2 to the 3n plus 1, and also we have p is divide n square. According to the divisibility statement, since we have n square is divide this number and p is divide n square, that means p is divide 2 to the 3n plus 1. Is called transitivity divisibility property. Okay, this one implies p is divide 2 to the 3n plus 1. It's equivalent, according to the divisibility statement, 2 to the 3n plus 1 is a congruent to 0 mod p. Okay, so I'm taking number 1 to the other side. I will get 2 to the 3n congruent to minus 1 mod p. Okay, since this one equal to this one equivalent according to the divisibility definition, so this means p is not divided 2 to the 3n. If p divided 2 to the 3n, it wouldn't have a minus 1 here. We should have 0 here in order to get p is divided this one. Okay, since we have minus 1 here, that means p is not divided 2 to the 3n. Okay, so now I'm ready to apply the Fermi theorem, because exactly is verifying the condition of this theorem, because p is a prime, is not divided as an integer 2 to the 3n, which is this one. P is not divided a, equivalent a to the p minus 1 congruent to 1 mod p. Okay, the same thing what happened here. This one is equivalent 2 to the 3n as an integer to the p minus 1 is the same thing as I have here, is a congruent to 1 mod p. Okay, I'm going to switch exponent here. I'm going to make some change in exponent here. Here I will get 2 3 to the p minus 1 to the n, okay, congruent to 1 mod p. This one in the same time. Now I can take n off from this one because I have 1 here. So I will have 2 to the 3 p minus 1 congruent to 1 mod p. Same thing I have, same thing if I'm going back to the original one. I'm going to raise n as an exponent. I will get to this one. Okay, so here is the first equation. Here is a first statement which I can use later. Here is the first one. Here is the second one. Okay, now I'm going to take these important formulas at the top and continue with our problem. In the last board I was working on divisibility statements, then I came up with these results. Now I'm ready to apply the Bayesian theorem. Okay, this step is more confused points because I'm going to make the combination between this one and this one. So now, since we know p is divide n, okay, that means p minus 1 not divide n. Okay, so because p was odd, now become even and n stays odd. Okay, so p minus 1 and n are not, so that's mean GCD of n and p minus 1 equal to 1. This one is verifying this Bayesian theorem for all x, y. In this case I'm taking x and y as non-negative integers. There is two integers numbers, which is this one, n and p minus 1, such that x is multiplied by n, x is multiplied by n minus p minus 1 is multiplied by y equal to GCD, which equal to 1. Okay, in this case I have chosen x and y are positive, that's why I put minus sign here. Okay, because x and y, it could be positive, it could be negative. I'm going to put this number to the right hand side of this equation. I will get x n equal to p minus 1 is multiplied by 1 plus 1. Okay, here is the third equation. Now I'm going to work on this statement. So we have 1 2 3 p minus 1 congruent to 1 mod p, or 1 is congruent to 2 3 p minus 1 as the same thing. So I have 1 is congruent to the 3 p minus 1. I'm going to transfer to the 3 to 8 congruent to p minus 1. So what I'm going to do now, I'm going to raise y as an exponent on both sides, 8 by both sides. Okay, so this is congruent 8 to y to p minus 1 plus 1. Okay, all are modulo p. 1 to the y equal to 1, so I will have 8 is congruent to 8 to y p minus 1 plus 1 mod p. So I'm going to replace this expression with this one. This one is verifying Bayesian equation. I will get 8 to the xn, 8 to the n, and exponent. This one equal to 8 to the n x. I'm changing the exponent. So this 8 to the n, I'm replacing 8 to the n equal to 2. 8 to the n is the same thing as 2 to the 3n to the x. Okay, so I'm going to replace 2 to the 3n with minus 1 mod p. I will get minus 1 to the x mod p. Okay, look at here in this Bayesian equation. We know number 1 is an odd, right? Is an odd, and we know n is an odd. So we know p is an odd, minus 1 is an even. So this term is an even. So the only way to have odd minus even is given as odd. That means this term is an odd. Since n is an odd, that means x is an odd as well. So x is an odd. Since x is an odd, when I'm taking the exponent off from this one, I will get minus 1. Congruent to minus 1 mod p. Okay, so I have 8 congruent to the minus 1 mod p. It's equivalent. I'm taking minus 1 to the left hand side. I will get 9 congruent to 0 mod p. What does mean? That means p is divide 9. Okay, since 9 is a multiple of p, 9 equal to 3 to the 2. That means p is divide 3 and divide 9. Okay, since p is divide n and p is divide n square, this implies p equal to 3. Okay, and the only solution that we have, n equal to 3 and n equal to 9. Okay, because 3 as a prime number is divide 3, that means p equal to n, and also the prime number is divide 9. If you plug number 3 into this expression, you will get 2 to the 9 plus 1 is divided by 9, is giving you 57, which is an integer. Okay, which is verifying this one. So if you plug n equal to 9, if you plug n equal to 9, is giving you 1,657,009. Okay, which is an integer as well. So I have 3 solutions. I have n equal to 1 as a solution, and you have n equal to 3, and I have n equal to 9. Okay, that's the only solution that I have. So I have done with this problem. Don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.